Okay, thank you, Sourabh. So, well, it's a pleasure for me to introduce. Well, we have a session with just one talk, but I think it will be very interesting. I have the pleasure to introduce Barkai from Birla University, and he will talk about non-normalized Boltzmann-Gibbs statistics. Please, Eli.
Okay, thank you very much. Thank you for the invitation. So this talk will discuss a marriage between two theories. And one of them is well known, and that's Boltzmann-Gibbs statistics. And the other one is actually coming from mathematics. It's called the infinite ergodic theory. And I'll be discussing the relations between these two theories, combine them together. This work was done in collaboration with David Kessler and Erez Agion. So at the beginning, I'm going to recap very briefly the Boltzmann-Gibbs statistics and what I mean by ergodic theory using a single particle description. Very simple. This will help us just with the notation. I will then show that in well-known examples or explain why and when, in many cases, the partition function of the system diverges, and this leads to Boltzmann-Gibbs states which are not normalized. This will just be some motivation. And then the two other parts of the talk are discussing a situation where the partition function is diverging, but still we can relate between ensemble and time averages. And I'll be discussing also some thermodynamic relations that are found in this regime of Boltzmann-Gibbs statistics. So to start, let us just remind ourselves what is ergodicity in this talk at least. We have here a Brownian particle attached to some spring, and it is in contact with the heat bath at temperature T. So my setting will be the canonical setting. This small bead is fluctuating in time around its equilibrium value. So you have some stochastic function of time. And then I can do, in general, I can do many experiments, but I will consider two types. One of them would be to consider an ensemble of these particles and then plot the distribution here of this position of this particle. And as you all know, because the spring is assumed to be harmonic, the force field is harmonic, and then the Boltzmann-Gibbs statistics is giving you a Gaussian distribution where the width is determined by the temperature of the system. On the other hand, I can also take this path and I can perform, let's say, a long time average, either over x or x squared, etc. And in the long time limit, the time averages and the ensemble averages calculated from the Boltzmann statistics will be identical, and initial conditions are of course wiped out and forgotten. So to recap, just repeating, but with equations, in thermal equilibrium for one-dimensional system in a confining potential, V of x, in the long time limit, we have some very famous Boltzmann statistics. The position of the particle is determined by the exponential of the energy divided by temperature, and temperature, energy is the potential energy of the confining system. The normalization, this Z here, is simply the integral over this thing. And I'll be talking about cases where this diverges actually. What does the ergodic hypothesis say? It says that the time averages, which I'll denote in this talk with this overbar, which is the integral of this observable. The observable can be many different things, which is a functional of the path, the stochastic path. If you integrate this over time and take the time to be long, divide by measurement time, this is the same as the ensemble average. And the ensemble averages are calculated from the equilibrium measure. Just as written here, you take your observable, you multiply by the Boltzmann function, you divide by the normalization, and you integrate. Okay, all this is well known in textbooks, but now let us consider a very well-known system. And this was considered by Fermi in 1924 at the beginning of the quantum revolution. And this will be a motivation for some case where normalization is not happening, and very simple case, a very well-known case, which is the hydrogen atom. So as you know, the hydrogen atom in the classical world, you have acceleration, and then according to Maxwell, it will radiate, and then the electron will collapse on the proton. And then, of course, quantum theory was a very successful theory, as it predicted that the electron will not collapse, that the size of the atom will be roughly the radius of Bohr, and this saved us from this catastrophe of collapsing of the electron on the proton. This was, of course, the idea of Niels Bohr, but then in 1924, Fermi wrote a paper on this quantum theory, and he says this is of course correct, and of course the quantum theory is of course valid. However, there is another problem, which is that according to thermodynamics, if you believe thermodynamics and the canonical ensemble, the size of this atom should not be zero, should not be finite, it should actually diverges. And then what Fermi says here, it's written in German, but I'll translate you, he takes the energy levels of the quantum particle, which go like 1 over n squared in our language, and this is the probability. And then he says, okay, let us sum this. This is the partition function. So we sum it. But because of the energy levels going like 1 over n squared, it's very easy to understand that the partition function diverges. He says this, diverges here. And the conclusion here is simple, that if you couple an atom to a heat bath, because the Coulomb potential is not binding, it goes to a constant at large distances, this system is not stable in the canonical setting. And the same is true if you think about Earth, and if you think this is a thermal system, then everyone in high school maybe has been taught that the density of particles above the surface of Earth is decaying exponentially. This is a Fermi's barometric formula with the distance divided by K Boltzmann T. However, this is true only if Earth would be infinite and flat, because eventually the force will decay, and then all the atmosphere in principle should be gone to hell, because again, the normalization, the partition function is infinite in these systems. This is the reason why in statistical physics textbooks, you usually don't teach these type of problems. This is only one example of diverging partition function. There is another well-known case, which is due to the work of Jean-Philippe Bouchot in the context of glassy dynamics. So I'm not going to go into details, but he considers a system which is in thermal equilibrium with some traps whose depth is E, but the density of states given here is exponential itself. So you have exponential density of states and you have exponential Boltzmann factor. And then if the temperature, the real temperature of the system is T, is less than this TG, TG is a measure of disorder, some number, then the partition function diverges. And what Jean-Philippe Bouchot showed was in the context of glassy systems that this is can be used when you talk about the dynamics, about correlation functions, etc. This limit where the partition function diverges can be described at least phenomenologically certain aspects of glassy dynamics. So in physics, this divergent partition function is very common. Many authors introduce some cutoffs to solve this problem, but in math, these people, they have a different idea. They are going to use a density which is not normalized, and I'm influenced by this infinite ergodic theory. So just to think about the specific experiments I have in mind, consider a surface. This is an experiment done by the Schwarz group. You have a surface. The surface, above the surface, you have a particle, and this particle is attaching and detaching from the surface, and it's going into the bulk. The bulk itself is just, let's say, plain water at temperature T. So if you look at the distance of this single molecule from the surface, it is attached more or less, and then it goes in the bulk, etc., etc. And assuming that the molecule and the surface are not charged, you have some attraction back, but eventually the force between the surface and the particle will be vanishing at large distances. The potential will go to a constant. And then you again will have the Boltzmann factor of this system is not normalized, meaning actually that the particle will eventually escape to infinity. But still, you can imagine, and I'll soon explain why, that certain notions of ergodicity of Boltzmann-Gibbs are still remaining, even though this system is infinite in the x direction. So let us explain intuitively why there is a relation between Boltzmann-Gibbs statistics and non-normalized states. So I'm going to consider a problem that you all know, and that is Brownian motion satisfying fluctuation dissipation in a potential field that looks something like this. The exact shape is not important, but what is important is that the potential goes to zero at, let's say here, at minus infinity and plus infinity. Because the potential goes to zero, the force at infinity is zero. This is not bounded motion. The partition function here is infinity. Now, I want to consider two observers. One I call the lazy observer, and one is the laboratory observer. The laboratory observer, I have here two lines. It's a little bit difficult to see. He looks at this part of the system, but let's say he can look at all the paths. So he looks at this path, and then the particle goes outside here, and it comes back, it goes outside, etc., interacting with the medium, which is at temperature T. Now consider a lazy observer, and he does the following. The particle goes here, and once you go out of your domain of view, you go out of here, you simply go smoke a cigarette, and you don't look at the trajectory here. You don't look at these red parts. So this trajectory was here, I copy it here, then it comes back after some time in this lazy laboratory time frame, it goes back here, etc. Now, if you look at this trajectory, it immediately tells you the following thing. This is like a particle with reflecting boundary conditions on this domain of observation of the particle. So the particle here for the lazy observer is like a system in equilibrium with reflecting boundary conditions, even though the real system is kind of infinite and there's no normalization. And you can imagine that here, inside here, you will have some Boltzmann equilibrium notion. If you don't believe me, you can do simple simulations, and before we do the theory.
But
and
Eli, one question is there. So there in these two situations, when you consider this reflecting boundary condition, so reflection is instantaneous, right?
The reflection is what?
The reflection is instantaneous when you talk about reflection, reflectory boundary conditions.
Right, but remember that in the real system, there's no real reflection. I just look at the part of the system, and yes, but you can think about it as instantaneous, yes.
Yeah, but in the left-hand side, when the particle goes out of this dotted line, and then it does follow this red path, so it will spend some time, which is typically more than the time that it takes to get the reflection.
Right, but I define here a lazy time, which is once you go out, you stop your clock. Okay. Once it comes in, you continue. And this is why you see this path reach this time, while this path is much further away. It's just a way to think about this. Now let us go into the details of the theory. So you can do this very simple experiment in numerical at least. Let us consider two potentials. This is the potential 1, and this potential stretches to plus infinity and minus infinity. And again, you have a temperature, you have viscosity, etc., and you have a Brownian motion inside. But the observer is looking only here on this yellow part of the system. So you have many particles at the beginning inside here. Some of them escape to infinity, maybe even most of them, but you have so many that some of them are left here inside. Then you look at the density. And then you have another experiment, exactly the same experiment, but instead of this zone that you are looking at, you have reflecting boundary conditions here. In this case of reflecting boundary condition and this potential, the Boltzmann state will have these two peaks corresponding to these two minima. And if you do this experiment where the number of particles in the observation domain is reducing, but you just look on those who remain behind, it will be this shape. And this shape and that shape are exactly the same. There is no difference. So while this system is infinite, it has no normalization condition, etc., the density of those particles who remained behind is exactly the same like the usual Boltzmann-Gibbs statistic. And this implies that many features of thermodynamics, stochastic thermodynamics, etc., can be defined if we look at these non-normalized states. And now I'm going to do the more mathematical part of the talk. So let us go. So we look at an overdamped Brownian motion in a potential field. So this is the force field with white noise. And importantly, the fluctuation dissipation between the diffusion constant and the damping is present. Einstein relations hold. Then we have a Fokker-Planck equation. And for illustrations, I'm going to use a Lennard-Jones potential. So X is going to be positive. So I guess you all know what I mean by Lennard-Jones. It goes to 0 at large distances. Later, if I have time, I'll also discuss a logarithmic potential, but all these potentials, what is special about them is that the partition function diverges. Now, the first thing to do, you have this Fokker-Planck equation that what we do usually to find the steady state is to say, okay, the density, the time derivative of the density is equal to 0. So a mathematical solution of this, even if you are not normalized, is this solution. But then usually this constant here is the normalization. And now we are not normalizable. So many people, including myself at the beginning, say, okay, this solution is not normalizable. Let's throw it to the trash. Well, this is wrong. So what is happening? What is happening if you cannot normalize it? So the claim is that I'm going to discuss now is that in nature, I want to think about different types of potentials. Here I plot them only in one dimension. So you have this harmonic potential where the partition function is finite. You have a log potential that if the strength of this log potential is weak enough and the temperature high enough, the partition function also diverges. Here you have potentials which are flat, or this Lennard-Jones potential, which is flat. Then you have other classes like x to the power 3 and minus x squared. Now, what I'm going to claim is that this guy has usual type of statistical physics. These three examples, because the potential is flat, for example, the particle can come back many times, will form what I will call special type of Boltzmann-Gibbs statistics, which is non-normalized. On the other hand, these potentials, where the particle can simply escape to infinity rather easily because of the force, these will be simply not in the domain at all of Boltzmann-Gibbs statistics. So this is a new classification of Boltzmann-Gibbs statistics. You have normalized states, non-normalized states, and other states which are not recurrent. The path does not return. So to see this, or to start see this, let us consider again the Fokker-Planck equation. And again, the potential is infinity, at infinity is 0. Then hand-wavingly, I'm going to look at position x, which is much smaller than the length scale of diffusion, which grows in time. And then I want to claim that this is the solution. You have pt of x, it depends on time, t to the minus alpha times the Boltzmann factor. Why do I claim this, at least hand-wavingly, is because when I act with the Fokker-Planck operator on this thing, I get 0. On the other hand, when I take the time derivative in the Fokker-Planck equation over this, I get t to the minus alpha minus 1, which is lower order in time, in the long time limit. So now the question is, what is this alpha? And this is actually very simple in this example, because for large x, what you expect and you indeed get is simple diffusion, because there the potential is not present. And that's the reason why the normalized density, perfectly normalized density, this alpha is going to be half. And then you can say, okay, I'm going to match the short x behavior with the large x behavior. What is the large x behavior? It's simple diffusion because the potential is not there. So the uniform solution given by this expression is very simple. You have diffusion describing essentially large distances, and you have the Boltzmann factor describing the short distances. And here you have something which is normalization, but this is the normalization due to the diffusion, which is just increasing here like square root of time t. Now, this was extremely short. We could prove this in generality using an eigenfunction expansion of the Fokker-Planck equation, something that I do not do here. So let us look at this solution, assuming you believe me that this is correct. In the long time limit, where I fix the position x, this Gaussian factor describing diffusion is simply 1, because t I take here to infinity. So if I have any asymptotically flat potential, then I get this very simple equation. The limit t to infinity of this function z of t, z is for similar to partition function in some sense, times the normalized density is given by this factor. Now, what is different than usual statistical physics? This is, of course, well known in statistical physics, is two things. One is that zt now is not a constant, it is time dependent. Secondly, this thing is not normalized. And this is here very obvious because I take a normalized function, I multiply it by something that increases with time, like square root of time, take time to infinity. So this function, of course, is not normalized. The point is that many forces in nature decay at large distances, and that's maybe this is in fact general. So now I just briefly will mention that it's very important that the potential will be flat, that the spectrum will be continuous. So for example, if I take this potential, which is negative of minus x squared, which is an unstable harmonic oscillator, so to say, one can solve the Fokker-Planck exactly with some initial condition. I can take the time t to infinity and multiply it by some time-dependent factor, but then I get something very different. I get something that depends on the initial condition. So the fact that I took z of t in my previous graph here, some function of time, multiply this, and this side is not dependent on the initial condition, is specific to the classes of potentials where you come back to the origin, you sample many times the origin, you are recurrent, so to say. Okay, so we have this very strange non-normalized states. The question is, what can we do with it? And the answer, the short answer is, we can calculate both time averages, which are slightly more complicated than what I'm going to discuss now, which are ensemble averages. So let us consider an ensemble average. Well, it's simply given by some observable OX times this density. This is the normalized density. But I'm interested in this thing, in this object, whatever OX is, in the long time limit. So it's very simple. I can replace here the time integration with the, I can replace this function, this density, with the approximation, which is given here by this Boltzmann factor, again, not normalized, divided by z of t, which is acting like a normalization, and then integrate. And what do I have here in this integral? It's very simple. It's just the observable times this Boltzmann factor dx, whatever that is, provided that this is a finite number. Then we call this observable integrable with respect to this Boltzmann factor. So again, the idea here that the observable itself, even though if I took the observable to be 1, this integral would be infinity. But the observable itself cures the non-integrability or the diverging partition function, and then this integral is finite, and then this gives you the ensemble average, just like you do any calculation of ensemble average when this is a normalized thing. Now the question is what are these observables that this integral exists? And the answer in our example is that many observables are suited to this. For example, the energy itself, because it goes to 0 at large distances, is an integrable observable. It will, if you plug in here the potential, it will give you a finite number and it will give you the ensemble average. We will show another example of the Virial Theorem. There are many examples like occupation times, pulse functions, many observables are integrable. There are other observables like x squared, which are sensitive to the diffusion for the large x behavior of the density, which are non-integrable. We will not discuss these observables here. So this theory of infinite ergodic theory very much depends on what is your observable. And there's the classification based on it. So let us see this at work. So I take this Lennard-Jones potential, I simulate particles, they all start here in at the center, they follow Langevin dynamic with some temperature T, roughly 1/4 of the depth of this small minima. And then I take the density of particles, I multiply it by square root of z of t, which again increases like t to the half. And then in the long time limit, I get this peak. This peak corresponds to this minima. And this function is not normalized, of course, and it goes to 1, to unity, because exponential of the potential is going to e to the 0, this goes to 1. Now you see here different dots, let's say this one compared to this one, these are the short time dynamics. So in the long time limit, you converge to this non-normalized state. The area underneath this curve is going to be infinity, as I just talked in the examples. But this is all set up for different machinery of statistical physics, I would say. And I'll give you one example or two examples if I have time. And one of them is the Virial Theorem, which I like. So the usual idea is that I can relate this multiplication of the force times x with temperature T. And x times fx, if you think about it a little bit, in my example, at large distances goes to 0 because the potential goes to 0. And this is going to be assumption. So this observable is an integrable observable. You calculate it with this non-normalized states. Here I multiply this by z of t, by the normalization, so to say. And I get this expression that this is proportional to k Boltzmann t times this L0. And what is this L0? L0 is the virial coefficient. Now, to prove this is one line of algebra. It's very straightforward. It by itself, I want to claim, is not so useful. I want to explain it in depth. So how do you do it? You take x fx and you need to integrate. You have this non-normalized states. You add a -1. You take the derivative with respect to x. You integrate by parts and you get this. But what does this Virial theorem really tell you about the system? Especially what is the meaning of this L0? So here I just showed you that the infinite density, the equilibrium properties in my language can give you this L0, but what does it tell us really? So to understand this, you need to go far beyond this talk and you need to look at the large X behavior. And you look at the large X behavior of the density, and as I said before, it's going to be described by simple diffusion. You then, then you use an eigenfunction expansion that demands a lot of work, and you look at the corrections to this term. So because you are not really diffusing, because you have a force field in this problem, it's weak asymptotically, but it's there, you can show that the corrections to the Gaussian are given by this L0 that appeared in the Virial theorem times x divided by 2 dt. So by the equilibrium properties, by this infinite density, I can calculate this L0 very quickly. And then I can use it to know, depending on your potential, what are these corrections to the Gaussian central limit theorem. I can also formulate this in a different way. I can take the mean square displacement, subtract 2 dt. Now, in the very long time limit, this thing will go, x squared will go to this limit because eventually you are diffusing. But if I look at the difference, the corrections, divide by this scale, which is related to z of t, I will get this L0. So this means I can get L0, which in two ways. One is in a measurement, for example, and the other way is by using this non-normalized state, I can calculate this length scale, which depends, of course, on the potential. So again, this is the virial coefficient, a Virial theorem in action. So we have this type of potential, it's flat. This is the infinite density. It's not normalized. It goes here to 1. I multiply here the usual density by z of t. Then I look at this observable xfx. I can calculate it with the non-normalized states. And then I can do simulation, these green lines, and it will nicely converge to the theory based on the non-normalized Boltzmann state. More exciting are these time averages, because time averages are stochastic variables. They are fluctuating here. So first, let us look at the mean of the time average. And this mean of the time average, so you see the line here is the time average. Then I look at many trajectories and I ensemble average them. And then you can show that this one is equal to 1 over t by definition. Here you have the ensemble average. But again, the ensemble average I just showed you is given by the infinite density. I can calculate this object as I just now showed you, if I know the infinite density, the non-normalized Boltzmann state.
Eli, you have 5 minutes.
Okay, sure, thank you. Then I can do the integral. Now recall that in our example, this average is decaying like inversely proportional to the partition function z of t, like inversely to 1 over t to the half, like here. Integrating over 1 over t, 1 over square root of t is very easy, and it will give you this factor 2. So this says that the time averages, these time averages are related to the ensemble averages, but there is a factor 2. And more generally, the time averages are related to the ensemble averages, like 1 over alpha, and alpha can be anything between 0 and 1. This 2 here comes from the fact that when the probability of return to the origin, the probability to be on the origin is decaying like time t in the square root, 1 over square root of time t. So 2 is an example, but in general, you have this relation. This is, in our case, the ratio is 2. So here I have, for example, the time average energy. Again, ensemble average, and it goes to this constant, to this factor 2. Again, this is quite easy to prove. We have also a entropy maximum principle. So we can define entropy by P log P integration. And then we add here constraints like we do in statistical mechanics. This is in the canonical setting. We have the average energy, we have the normalization, and we have one more constraint. That is the central limit theorem constraint that the x squared goes like 2 dt. I'm not going into details, but if you take the extremum of this, it's very easy to get back our original equation where the density is a multiplication of the Boltzmann factor times the Gaussian propagation describing the large X behavior. We can then describe the entropy, and this is given by this expression. So the entropy is the leading term is simply increasing like log of t, like in diffusive process. But if you look also at the other terms, which are smaller, these are given by the average energy, and a correction term here, which is also easy to understand. So the idea here is that, and this average energy, this is my point, this average energy you calculate with the non-normalized Boltzmann state. And you can do a simple simulation, and this is this blue line is the long time diffusive limit. So this will be the line also for free Brownian particle. It will converge to that. This is the simulation. But these corrections due to the energy, because assuming that the potential is not zero everywhere, are important. And you see, they give you these correction terms, though in the very long time limit, this entropy will be the same as the entropy of the free particle. So you can also show that if the usual thermodynamic quantity like ds, dE is equal 1 over t, but now when t is finite. So t is like a box in some sense here. I will stop here. We can also rephrase this in a different way. Delta S, what is delta S? Delta S is the difference between the entropy of the system with the potential and the entropy of a free particle is equal to the average energy divided by temperature. What does this say? This average energy, because of the non-confining nature of the potential, is actually decreasing. This average energy is also calculated with the non-normalized Boltzmann state. So the difference between the free particle and the particle with this weak potential is decreasing in time, but you can calculate this difference and it will be smack equal to the average energy, which again you can calculate with the non-normalized Boltzmann-Gibbs states. And here I'll also mention Farago. There are many works on the time averages, on the stochastic aspect, but I don't have time. I just pointed out that there are different classes of potentials that give you either infinite ergodic theory or ergodic theory, and I will just leave here some references and thank again Erez Agion and David Kessler for their work, and thank you for the attention.
Thank you very much. Thank you, Eli. Very nice talk. So it's time for questions. We have. Please raise your hand or use the microphone. If not, maybe I can start with. Yeah, I will. There is something that always surprised me, and it's not. I don't know if you can say something about it. It's this argument that you can find in the undergraduate textbooks that compare the thermal velocity with the escape velocity, and then they can predict the composition of the atmosphere of planets. Do you know that, Eli?
I know this, but okay, yes, I know a little bit about it.
Well, you just compare kT divided by m squared of the thermal velocity with the escape velocity from the atmosphere, from the gravitational field. And then you can predict, for instance, that the hydrogen escapes from Earth, but is trapped by Jupiter and things like that. And it works very well, which, yeah. Which is surprising. But of course, this is more complicated because it's not uniform temperature. So I guess, but I don't know if you can address this problem with this. Because in principle, any atmosphere is unstable, no?
Exactly. So I totally agree that in principle, any atmosphere is not stable. Of course, there are two answers for this. One of them is it's not stable on some what time scale. So if this time scale is extremely large, that is the barrier that you need to cross is very big and it will be a very rare event, then you can forget about the fact that you are not normalized. So going back to my example, and we also have works on this with Luciano. Going back to my example, so if I have here a potential, you see here, which is flat, but I go and take this potential very, very deep compared to K Boltzmann T, then the particle will simply stay inside here for very, very long times before it escapes. Now, it's true that if you take the long time limit, it will escape and then come back, and then my theory will be valid. But I assumed that it will kind of be able at all to escape. So I think that many atmospheres are really in a kind of very, very deep potential if the mass of the planet is very big. And then, you know, it will take them the age of the universe to escape. But I also totally agree with what you say, because this depends on scale. It will depend on what is the temperature, what is the mass of the planet, where you are looking, and of course, as you mentioned, also on the non-equilibrium nature of this real atmosphere. So it depends on some conditions, if you see what I mean.
Yeah. But what it is amazing is that this simple argument works very well. It can predict the composition of the atmosphere of many planets. Yes,
but they apply it to those atmospheres that exist. So
that's true. No, that's true.
So they are biased. So there are planets that it doesn't exist, and because, yeah.
Okay, more questions? So maybe just one, because now that you mentioned this problem of the well and so on, I'm surprised that this prefactor, this ZT, is only depends on the diffusion, but not on the shape of the potential. And,
Right.
and now your intuitive explanation tells you something that, because this factor is how it decreases the population around the origin, no, around the.
Right, but
So
first of,
it is surprising that does not depend on the well and on B.
well, first of all, this is all true provided that you are working at the long time limit, and the reason is that the time to return is controlled by this trajectory that you go outside, and here the potential is not important. So that's the reason why this factor is independent. So we work, for example, what will happen if you have, let's say, instead of these flat potentials, let's say you have a periodic potential. Then the return back will depend also on this Z of t will depend on the shape of the potential here. And you have to renormalize the diffusion constant that I had in this formula. It still grows like square root of t, but instead of d, you have some d star, which depends on the potential. And similarly, if I add here some potential, let's say a random potential, but again, you come back, then what you say is correct. The prefactor or the potential itself will modify the prefactor there. But for our discussion, where you have this flat potential, just simple diffusion wins over. So yes, you are right. In more general setting, the prefactor will work, but we did it, but I did not talk about these classes here.
Okay, so thank you. And is there question? Yeah.
Yeah, hi, Rahul here. So I was just wondering, I don't know whether you talked about it because I missed the first initial part of your talk. So for such potentials, can we also talk about the first passage time problem and those properties?
Yes, so, okay, you missed the first part, but actually I missed the last part. So the last part of the talk was exactly on this. And if you are interested, you can read more, but I just briefly state that the first passage times are actually super important here. Especially for when you would start calculating the time averages, which I did not have time. So the time averages are related to the first passage times because the statistics of the first passage time. And the answer to your question is yes, I can calculate the first passage times. They themselves, because the particle can escape to infinity, will decay like the first passage time to the -3/2. And this is exactly like normal diffusion. And it's super important that the average time of return diverges here, because the average time of the time diverges. It means that usual ergodic theory doesn't hold, because if for example, the time to return would be finite, the first passage time would be finite, like in this example of the harmonic case, you will go immediately into the in the usual case. So to put this a bit differently, in this equation that I just briefly mentioned, that the ratio of the time averages, this alpha is related to the power law decay of the first passage time. In usual diffusion, it's 1/2. So you get here 2, but there are other cases where you are recurrent and the first passage time is not 1/2. This exponent is not 1/2. And this controls this number here. So yes, this is super important. Again, it's in our papers. It's actually most of our work is on that.
Okay, thank you.
Thank you, Rahul. Any further questions? If not, well, let's thanks again, Eli, and thank you very much for the nice talk. And I don't know if the organizers want to say something. Sourabh?
Yeah, so thank you everyone for chairing the session, and thank you, Eli, for that interesting talk. So,
thank you very much.